between any 2 points as time moves forward, because the space is growing for some unknown reason. This implies that sometime in the distant past, the distance between any 2 points was 0, and the density of the universe was infinite. Because if you run things backwards, eventually everything collapses down to 1 point. And so you might think, well, how does that happen? Like, why would they collapse down to 1 point at the same time? Well, if you think about it, if something's twice as far away, it's moving twice as fast. Therefore, it will cover the distance back to where you are in exactly the same amount of time. Because if you have to go twice as far, but you're going twice as fast, you get there at the same time. If you're 3 times farther away, but you're going 3 times faster, you'll arrive back at the beginning at the same time as well. And so even though the stuff that's farther away, like if we sort of ran the universe backwards, would come shooting in at a higher speed, it would all converge down to the same point at the same time. Because again, if you're 10 times farther away, you're going 10 times as fast. And so if we ran the universe backwards, even though things are going different speed and they're different distances away, all of that would cancel out and everything would just come down to 1 point all at once. And so the origin, the expansion of the universe from this beginning is called the Big Bang. It's not like when Hubble discovered this, like they wanted the Big Bang. It just seemed like it was a logical conclusion from what we observed. And I do like to point out that when they were debating this, there was 2 theories about the universe. There was the steady state universe, which said that the universe was infinite and always had been and always was. And that was the current theory that actually Einstein believed in, which is one reason why he didn't actually get right on board with the Big Bang theory. And then the Big Bang people came up with the Hubble's law. And Fred Hoyle, who was a person who was arguing against the Big Bang theory, it didn't have a name yet. And so Fred Hoyle said in this debate, well, I can't be made to believe that the universe started in some Big Bang, like sort of deriding the theory with like sort of an insulting name. And the people who liked the theory said, hey, Big Bang, that's a good name. We're going to use it, even though like you said it in like a disparaging way. And I would argue Big Bang's a great name, because it's 2 simple words put together that make sort of like, like it's not that, like if it was like the expansional, origin of the universe, people are like, that sounds boring. But Big Bang it's a great name, because it's simple. Black hole, which what you'll learn about next week, that's another great name, because it's 2 simple words put together, but it has like an air of mystery and wonder about it, and it's not too complicated. Okay, so the Big Bang theory came from this. So, okay, where then is where is the center of the expansion? How far from the Big Bang? How far are we from the Big Bang? The universe has no center. The entire universe was created by the Big Bang. Okay, and they're not expanding away from a central point. So everything, like in this room, the Andromeda Galaxy, if you recollapse everything back down to 1 point, that entire point was the universe. So everything in the universe now was at the Big Bang then. And the way it's kind of hard to think of this, is that before the Big Bang, there was nothing. And by nothing, so if I ask people to imagine nothing, so imagine nothing, and then I say, okay, you're imagining something, you have to get rid of that too. Okay? Because before the Big Bang, there was no space, there was no time, there was literally nothing. Like, it wasn't like we had some empty universe pregnant, waiting for the Big Bang to happen, and boom, it happens. There was no universe. There was no space, there was no time. Everything that we know was created by the Big Bang. Okay? And so where is so if you blow up a balloon, for instance, if you're living on the surface of a balloon and it gets bigger, there is no center to the surface of the balloon. Like everything is just moving away from everything else. Okay? And so, as I said, it's incorrect to think of the Big Bang as an explosion from a single point. Since the entire universe was created by the Big Bang, including all of space and time, the explosion occurred everywhere at once. It happened in this room, it happened as far away as we can see, it happened everywhere. So as I said, the universe is not expanding to some empty space beyond the galaxies, because the space was created by the Big Bang. And so, if I... Let me see if I can... I'm going to speed this up. That's even worse. Okay. And so what most people think is, like you had this, and so I'm going to just draw some Cartesian. And so the Big Bang happened, so like we had this empty universe, and say the Big Bang happened there, and it started, expanding out into more and more previously unoccupied space, like there was pre-existing space. That's wrong. Okay? This is the way you think of an explosion, like a firework going off, where it blows up and it expands and makes more space. This is wrong, okay? The idea is that the Big Bang, if it was this, if I put my little tic-tac-toe thing in there, what happens is, as the universe gets bigger, I don't gain more boxes, the boxes just get larger. Like it's blowing up from the inside out. And so if you put two galaxies, like one here and one here, but it's later on here and here, they're moving apart because the boxes are getting bigger. Not because they're actually physically moving apart. Like they're not flying through empty space here. They're moving apart, and the more boxes that are between you, the more growth you get in the same amount of time. Just like the rubber ruler. Okay? And so as I said, what came before the Big Bang? Since all of our laws of physics were created, we cannot use them to probe backwards to time before the Big Bang occurred. Are there parallel universes? For example, my parallel identities get an A+ in all my high school classes. Well, again, our laws of physics only apply to our universe and are contained within it. We may not be able to use them to probe the existence of other universes beyond our own. So we can't answer that question. Okay? So, as I said, in fact, the expansion of the universe is the expansion of space itself. A better way to think about the expansion of the universe is not that distant galaxies are moving away from us, but they're stationary and the space between them is expanding. As I showed here, not like that. Okay? As the space between the galaxy expands, distant galaxies appear farther away. In addition, this expansion of space stretches the wavelengths of light as they travel, and this expansion is what actually creates the redshift. So when we see this Doppler effect, because the galaxies are moving away from us, okay, it's due to the fact that if you imagine putting like a sine wave on like a piece of elastic and you stretch it, then the wavelength of that sine wave is going to get bigger because of the stretching. So one way to think about the universe is the light coming from these distant galaxies is, for lack of a better description, sort of embedded in the universe. But as the universe grows, those wavelengths get stretched out. Okay? And so one way to think about, another way to, about the expansion of the universe, it gets back to the Hubble constant. People say, well, how fast is the universe expanding? When I took it into different units, I told you that the expansion of the universe was 13.5 miles per second per million light years. So what this means is, if we have a box that's a million light years across, and a million light years is really far. I mean, 1 light year is 6 trillion miles, so you have to multiply that by, so it would be 6 trillion million miles. That much space, so a million light years is getting bigger by 13.5 miles per second. Right, so every second, that million light years gets 13.5 miles larger. Right? Now, when you look at that as a percentage of a million light years, I mean, 1 light year is 6 trillion miles. You have to multiply that by a million to get a million light years, so 6 trillion, that's like 6 times 10 to the 15th miles. It's only getting bigger by 13.5, which as a proportion is incredibly small. Right? And the velocities only get large if you have a lot of these 13.5, a lot of these boxes between you. So the farther away you look, since there's more boxes growing, the faster the universe is expanding. Now eventually you get to a point where if you go enough boxes away, that the universe is expanding away from you at greater than the speed of light. Right? Because 13.5 miles per second per million light years, if you figured out, like, you could calculate, well, how many million light years would I have to look away, and that galaxy would be receding from us at greater than the speed of light, which means you'll never ever be able to see that galaxy. Right? Because I think you can see, if it's going away from you, even if light's coming back the other direction, it'll never get to you. It's like if I'm on a car going 100 miles an hour, I shoot a bullet backwards at 60, it doesn't go. Like, I can't hit somebody that's like down the road like that. It just doesn't work because the bullet's still moving, if I'm shooting it backwards, it's still going the wrong direction. Okay, so this is how we came up with the idea of the Big Bang. It came from the fact that we see the universe expanding And it seemed like, as I said, the best idea we can come up with is that, the universe formed by this, again, it's not really an explosion, but it burst into existence and started expanding in this way. And I realize I've used up all my time. Do we have any questions? I know you probably want to get some coffee and some snacks, but do we have any questions? I mean, I can do my best to try to answer them. Yeah?
I know you're saying that there's no like definite center of the universe, but like, is there not like one point where the distance to like the outer edge of the expansion or whatever is like the same?
No. Well, every point would see that, because to the outer edge, like, we don't know what the outer edge is, because if you have a view of the universe, and as we'll find out, I didn't get to it, like, from the Hubble constant, we can find out, like, what you can do is you can calculate how long would it take for everything to collapse back, and that's about 13.8 billion years. So the universe, we think, the Big Bang happened, we think, about 13.8 billion years ago. We don't really know how big the universe is, because if anything is greater than 13.8 billion light years away, the universe isn't old enough for that light to have gotten to us yet. And so therefore, what we have is, we have the visible universe, which is what we can see, which would be, and again I'm sort of shorthanding this, would be like 13.8 billion light years in radius. Outside of that, and we know we can't say anything about what's outside of that because there's no way to get scientific data. You can theorize about what it's like, but it's not science because science requires a test, and there's no way to test any idea. So like outside of 13.8 billion light years, it could be all bricks, or it could be turtles. And you couldn't prove to me that outside of 13.8 billion light years that the universe wasn't just chock full of turtles. I mean, I don't think that's true, but, and I wouldn't propose to say that it was true, but I couldn't prove that it wasn't true either. So this actually goes back to an ancient idea where people thought that the universe was like on the back of a turtle. And then people would say, oh, well, what is the turtle on? And the answer to that is it's just turtles all the way down, which of course makes no sense. But it gives you this idea that it's this like air of mystery. So it's like, so the universe is riding on an infinite stack of turtles, which who's standing on, we don't know what. Other questions? Yeah.
So you were talking about the galaxies expanding away from each other, but the galaxies themselves are expanding.
Right. No, gravity locally, like you're not getting bigger.
Yeah.
I mean, well, for one is because, like to even measure any reasonable amount of expansion, you have to be very large, like, as I said, like millions of light years.
Right.
But locally, gravity can overcome the effects of the expansion. So really the nearest thing that we can see where we can, like between us and the Andromeda Galaxy, the force of gravity and plus the fact that it's so close means we can't, like the things overcome. The nearest thing that we can see where we can actually observe the expansion of the universe is the Virgo cluster, where I showed you that giant M87, which is 60 million light years away. And actually one of those primary missions of the Hubble Space Telescope when it was built was the same stars that Hubble saw in the Andromeda Galaxy, so he was able to calculate a distance to the Andromeda Galaxy. The Hubble Space Telescope was designed so it could see those exact same stars in the Virgo cluster, which is 60 million light years away. Because if you could get a really we can see how fast the Virgo cluster is like moving away from us due to the expansion. But if you want to get a good measurement, you can see how fast they're moving, but you need to get a good distance to the Virgo cluster as well. Because you say, okay, we see how fast it's moving, but we want to know how fast is it moving per million light years, or like in other words, we want some ratio. And so the Hubble Space Telescope, one of the three primary missions when it was funded by Congress was to find what are called Cepheid variables in the Virgo cluster, which it actually did. And what that did was that nailed down the Hubble constant to a higher degree. Because, I hate to sound like an old fart, but when I was in school, like now we know the Hubble constant's like 71. When I was in school, it was like, well, it's somewhere between 50 and 100. So therefore, the universe is somewhere between 10 billion years and 20 billion years old, depending. Because the slower the universe is moving, the older it is. The faster it's moving to get those distances, the younger, because you can cover those distances more quickly, the faster it's moving. Do you have a question?
So everything has a redshift in the universe?
Well, pretty, like the Andromeda Galaxy is actually coming towards us. Like, we're gonna collide with the Andromeda Galaxy and somebody's gonna get eaten. But when you get beyond a certain distance, like the local gravitational effects give way to the overall expansion of the, like growth of space.
But
Like I said,
technically, the space is still growing.
space will, yeah, not only that, we don't, I mean, I guess this could be 2 lectures, but the thing that's weird about this is people thought that space would be slowing down. In other words, there was the Big Bang and expanded outward, and gravity would act like friction, which would slow down the expansion over time, like air resistance or something like that. And so people were trying to measure like how fast the universe was slowing down, because if you did that, you could determine if the universe was going to keep expanding forever, or if there was enough gravity, like gravity could stop the expansion and cause it to recollapse. And so the universe could be like bang, crunch, be like some big giant cosmic yo-yo. We could be on like the 100th iteration of this. I mean, we don't know that, because there are 2 sort of fates. Like either the universe is going to keep expanding forever, or it's going to collapse. I mean, and which one of those is dependent on how much mass there is in the universe. If there's enough mass, and also how powerful gravity, I mean, there's a number of parameters. But if there's enough mass, you could stop the expansion and recollapse. If there isn't, then it'll keep expanding forever. So people realized if I could figure out how fast the universe was slowing down, I could figure out what the mass of the universe is and then determine what the fate of the universe is. Well, what they found out was not only is the universe not slowing down, it's accelerating. Like the universe is expanding faster now than it was after the Big Bang. And we attribute this to something called dark energy, which we have absolutely no idea of what it is. And so astronomers deal with this by not thinking about it. Because we have no way to explain why the universe is speeding up. Because you can't speed up for free. Speeding up costs money. Well, it doesn't cost, it costs energy. Like you have to have something pushing on you to speed up. And you have more kinetic energy if you speed up. So that has to be coming from somewhere. And so we imagine we call that stuff dark energy. And it makes up 73% of our universe, and we have no idea what it is. Now the other thing is there's other stuff called dark mass. I'll just leave you with this. Dark matter makes up 24% of our universe. Okay? And if you add them, well, I think it's 72 and 24. And so dark matter is 24%, dark energy is 72%. Those add up to 96%, and we haven't the foggiest idea of what either of those are. So anytime you think like humans are getting like really smart and too big for our britches, just keep in mind we don't even know what 96% of our universe is. Like everything like you and me and planets and stars and all that stuff makes up at most 4%. Which I think as an astronomer, if you have something that's like really complicated and it's only like a 4% effect, like you would just ignore it. Because like 4%, I can deal with a 4% error, that's fine, right? But what I'm saying is like the other 96%, like we'd like to ignore that 4%, but that's the only thing we know anything about, right? And so, there's a ways to go. Let me put it that way. I mean, there's still a lot. I like this because it tells us there's lots of cool things out there that are just waiting for our brains to become sharp enough to figure out, which I think is good. I mean, it leaves you guys something to do later on in life, right? Like we haven't figured everything out. Okay. I realize I've gone over. Let's take our break now, and afterwards we're going to get back together. We're going to make some rockets, and there's a few other things that I want to chat about.